All right, so let's go over some questions from quiz 5. Let's start with question 1 here. Which X plus ion would have this type of 4-electron spectrum? So what we're told is X plus has this spectrum, right? And then that means our X, the neutral ion, should have one more electron than that, and then that has to go in as a p electron. Okay, so it's going to be one other peak over here. So it's going to look like that. Now, if we count the electrons, we have 2 plus 2 plus 6 plus 3, 13 electrons. When it is neutral, that means we have 13 protons when it is neutral. The element that has 13 protons, so the atomic number of 13 is aluminum. So our element has to be aluminum. Okay. Just do one other question like that. Okay. All right. Again, X2 plus has this 4-electron spectrum. Okay. That means our neutral element X must have 2 more electrons than what we see in the 4-electron spectrum. That means we can have another peak here. The P should be 3p subshell with 2 electrons. Okay. Altogether, we have 2 plus 2 plus 6 plus 4, 14 electrons in the neutral X element. That means we should have 14 protons in the neutral X element. Therefore, the one with 14 protons, or the atomic number of 14, must be silicon, and that's why the correct answer here is silicon 2 plus. Okay, here time on to a different type of question now. Okay, let's do this X minus. Okay, so if X minus has this 4-electron spectrum, and then the neutral X should have one less electron than what we see here in the 4-electron spectrum. Therefore, we are not going to see this. Instead, we're going to see only one electron in the neutral element. Right? So the neutral element has 2 plus 2 plus 6 plus 1, 11 electrons. The neutral element with 11 electrons, that means 11 protons, is sodium. Therefore, our correct answer must be sodium. Okay. Now, let's move on to the next question. Okay. It's about the atomic relative size of the elements. We have O2 minus, okay, and Na, neon, and sodium plus. Okay, O2 minus. What I'm going to do is I'm going to count the electrons and the protons. Okay, let's count the number of electrons of all of these species. O2 minus, Ne, and sodium plus. Okay, when it comes to the number of electrons, okay, O2 minus oxygen, when it's neutral, has 8 electrons. Now it has a 2 minus charge, that means it has 2 more electrons than the neutral atom. Therefore, it has altogether 10 electrons. Neon has the atomic number of neon is 10. Therefore, it has 10 protons and 10 electrons. And then sodium plus, sodium when it is neutral has 11 electrons. Now sodium plus should have 1 less electrons than that, therefore we should have 10. And then I'm going to look at the number of protons. Okay. Oxygen 2 minus has atomic number is 8, therefore it has 8 protons. Neon, the atomic number is 10. It has 10 protons. Sodium plus, the atomic number is 11, therefore it has 11 protons. Okay. So all of these species have the same number of electrons, but because you have more protons in the sodium plus nucleus, the electron cloud is strongly attracted towards the sodium nucleus. As a result of that, sodium will be the smallest ion, and then neon, and then O2 minus is the largest because it has the least number of protons. That means least positive charge in the nucleus. And as a result of that, the 10 protons, 10 electrons are least attracted towards the oxygen nucleus. Therefore, the electron cloud will be larger. And as a result of that, the ion will be larger. Okay. So in other words, we can explain this trend using the second option over here. They all have the same number of electrons, but the one with more protons, sodium plus here, will have the strongest attractive interactions towards the electron cloud. And as a result of that, that electron cloud will be the smallest. Okay? And that's why this is the correct answer. Okay. And if you look at the other wrong answers here, the down a group, the size increases due to valence electrons being filled to larger shells is a correct statement. However, it does not explain what is going on in this problem over here. Okay. And then the next and the third statement, they all have the same number of protons. It is incorrect. We don't have to read further. And then the fourth statement, down a group, the size decreases. That is also incorrect. Down a group, we know the size has to increase because we are adding shells, but it is not relevant to this anyway. Right, so, and then that's about question 2. And moving on to question 3. We're asking for the electron configuration of let's go to this question over here. What is the electron configuration of the atom of indium with an atomic number of 49? Okay, so what you need to do is you need to go to the periodic table and then locate indium, which is 49 over here, right? And then to find the electron configuration of that, to get to indium, which is over here, we need to complete the core shell of krypton. It's going to have the core shell of krypton, right? And then to get to indium, we need to fill all the electrons in S subshells. Right here, 1, 2, 3, 4, 5. In the fifth one, this should be 5s2. Okay, and all the electrons in the 4d subshell. Now it should be 4D, and then in the main group over here in India, only one electron in the P subshells are filled. Therefore, this should be P1. Okay, so if you write this down again, indium has the core shell of krypton. And then 5s2 is filled. Okay, remember this is S1 and this is S2. And then all the electrons in the D are filled. Okay, here are my D's. Okay, since we're in the fifth, since we're here, now we know this has to be the 4D, not 5D. I'm going to write 4D over here, 4D, and then in P, in 5P, you have one electron, right? And some people would like to rewrite this, having only the valence shell outside, right? So if you do that, 4D will be inside, compared to the valence shell, which is the fifth shell, so it should be 5s2, 5d1. Okay. Now we do is I'm going to go back to my question over here. So the correct answer for the indium electron configuration is krypton 5s2, 4d10, and 5p1. Okay, and then that's why this is the correct answer. Right, I'm going to clear that out, and then I'm going to move down to the next question, question 4. Given the data below, if atom X would react with atom Y, what is the formula of the molecules of the chemical compound that will likely be formed? Now, all we need to do here is just consider the valence shell, okay? And we know when it comes to 4-electron spectrum, they're showing all the electrons in the atomic structure. So we have the outermost shell, which is these electrons over here, okay? And these are my valence shell. Valence shell, okay? And then the inner shells are called core shells. Right. And when it comes to chemistry, all that matters is the valence shell. Okay, the core shell doesn't play a role when it comes to the chemistry. Okay, so I will only pay attention to this. Okay, now if you look at the valence shell, we have 2 plus 3, 5 electrons in the valence shell. Right. So so this is S2, right, and then P3. It's not that important now. All that matters is we have 5 electrons, right? But if we have a complete valence shell, then we're going to have 8 electrons. Okay, since we only have 5 electrons, that means we have 8 minus 5, or 3 vacancies in the valence shell. And the number of bonds commonly formed by an element is equal to the vacancies in the valence shell, or in this case, number 3. Okay, so this gives us the vacancies. Write that down. Vacancies. Okay, and then this is equal to the common bonding pattern, right? Common bonding pattern. The bonding capacity, the same thing of an element. Okay, now once we have the common bonding capacities, okay, so we have the common bonding capacity of element X is 3 because we have 3 vacancies, and Y has 5 electrons as well in the valence shell. Therefore, it's going to have 3 vacancies, so common bonding capacity must be 3. So both X and Y form 3 bonds each. Therefore, if we want to have a chemical compound between X and Y, okay, we only need 1 of each. For each X atom, okay, we would need only one Y atom. So it's going to look something like that. So the chemical formula must be X1. Okay, and then we move on to the next question. Okay, let's do this. All right, now again, the same scenario. All right, when it comes to X, in the valence shell, you have 5 electrons. That means you have 3 vacancies. That is going to form 3 bonds. When it comes to Y, when it comes to Y has 7 electrons in the valence shell. Right, that's 2 plus 5 is the number of valence electrons. Okay, and then therefore the vacancies must be 8 minus 7, which is 1. Therefore, since Y has 1 vacancy, the common bonding capacity of Y is 1. Okay, so for every 1X, which is gonna form 3 bonds, okay, you're gonna have at least 1 Y. Because Y can only form 1 bond. Now it's gonna look something like that. Therefore, the chemical formula must be X, Y, 3. Okay. With that, I'm gonna clear my blue line and move on to the next question. Is this guy over here? All right, which statement below correctly describes their relative atomic radii and first ionization energy when comparing selenium with tellurium? Right. Again, when to do this, we need to compare. We need to go to the periodic table and locate selenium and tellurium. Now, let me get them. So here's selenium, and then here's tellurium. Right. So selenium and tellurium are in the same group, right? But tellurium is below selenium. When you go down a group, the size of the atom increases. Therefore, the tellurium is going to be larger than selenium. And also, when you go down the group, electrons, since the atom gets larger, the valence shell electrons are going to be further away from the nucleus. Therefore, it will be easier to remove electrons. Therefore, the first ionization energy of tellurium will be smaller than that of selenium. Right? So again, down the group, you go down the group, okay, size increases, and then the first ionization energy, I'm going to call that F I E decreases. Okay. Now let's go back to the question. Right, and then if we look at the correct answer here, the atomic radius of tellurium is larger because it is one below selenium, and the first ionization energy of selenium is greater than that of tellurium. It's the correct answer. Okay, only other answer is something else. Okay, now one thing I could mention here is, now we are given a question like this. Before reading the answer options, if you can come up with your answer and compare that to the answer choices given in the question, I think you have a better chance of doing well in these problems. All right, let me try to clear my blue line. All right, let's go to the last question over here, question 6. All right, the question is, the energy level diagrams of different atoms are shown below. Which atom has the lowest ionization energy? Okay, so now this is very similar to the 4-electron spectrum again. Okay, so we have the lowest energy. So this is like the potential energy, right? So we have the first shell over here with the lowest potential energy because they are closest to the nucleus, and this is our first shell, shell 1, right? So shell 1. Yeah, it's called N equals 1. Okay, meaning shell 1. Okay. And then we have our second shell over here. Okay. This is our N equals 2 shell. Okay. Now, the idea of ionizing, the lowest ionizing energy is the energy required to remove an electron, right? Now, the idea is if you remove an electron, they are no longer attracted towards the nucleus, and as a result of that, the potential energy will be 0 of that particular electron, right? So if I go to the one more time, if you want to ionize an electron from say N equals 2 shell, and then this subshell, this has to be 2p subshell, and this is 2p, this is 2s, and then this is 1s. Okay, if you want to remove an electron from 2p, then that what that means is you're removing, or you're moving this electron, one electron from here to until the potential energy of that electron is zero. That means the attraction between that electron and the nucleus is zero. That's the idea, right? And then for atom A to remove electrons, you need to provide this energy, and for atom B, you have to provide this much energy. So you can see it is less. And then atom C, it is even less. Again, they're further away from the nucleus. And atom D, you need to provide a bit more energy than B and C, but less than A. So as you can see, it is easier to remove the energy required to remove remove electrons from C is low. Okay, in other words, the ionization energies for atom C must be lower than A, B, and D. That's the correct answer of the option C. Okay, let's do another one. Here. Now again, same diagrams. Which atom has the electrons with the lowest average potential energy? Lowest average, lower potential energy means stronger attraction, stronger attractive interactions, right? So closer you are to the nucleus, stronger the attractive interactions. If you look at these electrons, you have the lowest potential energies in atom A, okay? Because I mean they seem to have they seem to be closer to the nucleus. As a result of that, atom A will have this the lowest average potential energy. Okay, and then let's do the next question. Yeah, again the lowest average potential energy, the same one. Okay, this one, which atom is likely to form two bonds when forming molecules? Okay, so the number of bonds an atom can make is all about the vacancies in the valence shell. Okay. Now when it comes to atom A, here's my valence shell. You already have 8 electrons. There are 0 vacancies. So atom A is going to make 0 bonds, like a noble gas. Atom B has 1, 2, 3, 4, 5, 6 electrons. Therefore, 2 vacancies. Therefore, atom B is going to form 2 bonds. Atom C has 1, 2, 3, 4 electrons. Therefore, 4 vacancies. Therefore, it's going to form 4 bonds. And atom D has 1, 2, 3, 4, 5, 6, 7 electrons. Only 1 vacancy. Therefore, it's going to form 1 bond. So atom B will be forming 2 bonds. The correct answer is. Okay, so those are the answers, and then the concept behind the concept behind